To construct squared complex numbers, we first establish the squared modulus, which consequently stretches in a radial manner and stretches shapes inside the unit circle toward the origin. Then we double the argument. Now I say then, but we could very well do it the other way around. First, double the argument, which causes the small circles on the figure to bend, and only then elevate the squared modulus. If we do both at the same time, the conformity is kept all the way through. The circles on the figure remain circles. We will now demonstrate the z squared plus c operation for a chosen value of c that we will choose in a way that shall be described later on. We start with an initial value of z, and then we square it, which means squaring the modulus and doubling the argument and adding the additional value of c. Only then do we take the end value as the initial value, and we repeat. So rho gives rho squared, theta gives 2 theta plus c. Rho gives rho squared, theta gives 2 theta plus c. Square the modulus, double the angle, plus c. Square the modulus, double the angle, plus c. And we keep doing this operation to get the orbit of the initial value. And what eventually happens is that the point goes out of the screen. So the orbit stops there. Let's color these points in dark blue. Now let's take a new initial value and apply the same formula. Rho gives rho squared, theta gives 2 theta plus c. Rho gives rho squared, theta gives 2 theta plus c, etc. What happens then is that the orbit cycles, switching between 3 points. We always end up in the same positions. Let's color this orbit in red. We now have 2 orbits, one marked in dark blue and the other in red. Let's take a new initial value and see what happens. Eventually, it goes out of the screen. Mark it in dark blue. We take a new initial value, it cycles. Mark it in red. By taking a wide range of different initial values, we obtain many orbits. And when we mark all of the possible outcomes, a drawing is formed, which is named the rabbit. In technical terms, this will be called the filled-in Julia set of the complex polynomial. Let's take a closer look at it. Once we start wandering and looking around, we see the same shape everywhere. A pair of ears, one ear on the left, and another smaller one on the right. We find the same shape occurring on every border of the rabbit and at every scale. Once we zoom on a specific point, we see little to no change. These are properties we define when we say the rabbit shape has a fractal nature. Once we stop zooming, it's difficult to say what change there was, and how big of a zoom just happened. This raises 3 questions. What happens to the point that escapes? What happens to the points that cycle? And are there any orbits that do neither of the 2 presented patterns? For the points that escape, if we take a point in the blue area, its orbit will, after some time, go beyond the screen's borders. It can take some time before it does so, but once it does not take much time at all before it reaches farther than even the most recently found quasars. What happens to the points that cycle? Let's first note that 0 is periodic with period 3. 0 is the absolute center of symmetry of the rabbit shape. It is also the critical point, meaning the point whose derivative cancels out. Its image is c, because 0 squared plus c is c. Then it goes to c squared plus c, which ends up back to 0. This is how we determine the value of c. If another value had been taken, another shape would have appeared, marked here in pink. 0's image would have been this new value of c, and then c squared plus c, only to become c squared plus c all squared, which has no reason to be equal to 0. To make sure it is equal to 0, we have to modify the value of c such that the shape of the rabbit appears. This value of c is negative 0.12 plus 0.74i, and so on. Now let's take a set of points around 0. When the first operation is done, this set ends up compressed. The two last operations makes this set a little wider, but these do not compensate the compressing of the first operation, which it has on the first 2 points. This is because the operation z gives z squared, and therefore makes small values extremely small. And once c is added, it contracts the points together, around the point c. The set becomes smaller and smaller. This is what characterizes the attractive nature of the cycle, which in this case is very efficient. This means that according to linear simplification, the operation z equals z squared contracts all points to 0. We can color the rabbit shape depending on how quickly the points are attracted to the center of which. We can also color the exterior of the shape depending on how quickly the points escape the screen's borders. Third question. Are there points that are neither attracted to the cycle nor escape the screen completely? Amongst those are fixed points, for which z squared plus c equals z. This is a second-degree equation, which has 2 roots, alpha and beta. If we take the point negative alpha symmetric of alpha, that has the same image as alpha, which means that the point negative alpha crosses alpha and stays there. Now this negative alpha point has 2 reciprocal images. Each of these will first cross negative alpha and then alpha, which will stay on alpha. We can continue with this reverse process, and we get many points out of it. Infinitely many, in fact. Each of these is a point whose orbit crosses alpha and stays. They are then points that are never attracted by the center nor by infinity. The same thing goes for beta. Point negative beta has an image of beta, and once it crosses beta, it stays there. We can do the reverse process just like negative alpha, starting from negative beta. We then obtain 2 points per operation that will multiply out to infinity. We can also search for periodic points. If we take the periodic points of period 2, giving us z squared plus c, all squared plus c, equals z, we find the 2 alpha and beta points. But we also find a cycle between the 2 composed of gamma 1 and gamma 2. Gamma 1 has an image of gamma 2, and gamma 2 has an image of gamma 1. Now if we take the 2 points symmetric of gamma 1 and gamma 2, each of these will cross the cycle and stay there. Each of these new points will cross the cycle again. and we then obtain an infinity of points that all fall on the gamma cycle and stay on it. We can do this process for all periods. We then obtain, according to the algebraic process in successive layers, an infinity of points that are neither attracted by the center nor by the outer borders of the screen. But there's an uncountable infinity that we can see through a topological view. If we take a point in the red area, this point will be entirely surrounded in red. We say the set of red points is open. Similarly, if we zoom in on a blue point, all we will be able to see is blue. If we decide to trace a line that crosses a determined red point, this line will obviously contain a red point and a blue point. However, it'll also contain the border point that cannot be either red or blue. If we make the line slide, we can visualize an uncountable infinity of border points, which aren't attracted by either the center nor the outer borders of the screen. To find our way within this complex shape, we'll define each of these different components with an address. To do that, let's first take a look at the main three components, u, v, and w, those which contain the points attracted to by the cycle. To locate the point within the u component, we do as follows. We take a little sector from the origin, and we do the same for each of its reciprocal image. If we rotate each of these little segments, they will eventually all align, forming what's also called carets. We obtain a graduation of u's borders from 0 to 1, thanks to the internal arguments, with each of the carets pointing to an internal argument. 0, a quarter, half, 3/4, etc. We will use this system to give an address to each component, allowing us to label them uniquely. A component directly attached to u is defined by the internal argument of the point it is connected to, as well as 1 or 2, depending on which component we're talking about. 1 if the component is on the right, which in this case is what we have, or 2 if the other component is being defined. U 3/4, 2 will define the type 2 component located at 3/4 of a rotation around the center of U. The V and W components each have an address of U 0, 1 and U 0, 2, respectively. And for those not directly connected to U, we will write their address in different steps. First, we start from U. We write the internal argument at which the component is connected to U. Then we take this subcomponent and write at what internal argument we can find our destination component. U, 1/2, 1, 1/4, 2. We can also do it the other way around, starting from an address to find a specific component. To get the address written here, we start from the point U, rotate 3/4 of a rotation. This type 1 component is easily detected. And within this type 1 component, we do half of a rotation counterclockwise to find our smaller type 2 component. And within this smaller type 2 component, do 5/8 of a rotation to find our destination type 2 component. And we arrive at the point from the given address. This system is efficient because with such a small address, we end up with a fairly short address, and we can define a component that is, as it is, minuscule. There are thousands of components with the same size as this one. This system of addresses allows us to attribute a description of the dynamics of the rabbit, meaning how each component is connected to one another. The U component connects to the V component with twice the internal argument. When we fill in the radius of the U component, its image will fill the V component twice over. Therefore, we obtain an application of U and V, which isn't a bijection, but a type 2-1, where each point of V corresponds to two symmetric points in its reciprocal image. V's original shape can be transposed to W from a bijection, only to then be transposed to U's original shape, also from a bijection. If we take a component, one that's attached to U, at any given internal argument, in this case, 1/4, its image will be the same type component attached to V at double the original argument. Its image will then be the same type component attached to W, with the same internal value. We will then obtain the component attached to U with the same internal argument, still the same type of component. This component, W prime symmetric of W, has an image of U. Then, U is transposed to V. V is sent to W, and W to U, like so indefinitely. For any given component, it is not difficult to find its address by rewinding the pattern like so, to find the address of its image. By continuing this algorithm, we can find every component within the orbit of the component where we started from. All the addresses will eventually end up in this loop, jumping between the first three components, U, V, and W, which contain the points of the attractive cycle. U being twice the surface of V, jumping to W, only to be transposed back to U by the bijection. The Julia set, properly speaking, is an image of itself when we apply the 2-1 application. That's the application in which Z gives Z squared plus Z that consists of doing rho gives rho squared, which stretches the shape. Then theta gives 2 theta, which is the application of type 2-1, which gives the rabbit shape its original form, and the additional translation to put it back in its original spot. As mentioned before, we can very well start with theta to 2 theta, the type 2-1 application which reconstructs the rabbit shape in its entirety, although slightly bent, only to then apply rho to rho squared, which will correct this bend, and of course, the translation. We can do both at the same time to keep this movement fluid. But regardless of that, you only need half the rabbit to have the rest of the shape. You can obtain this half by cutting the rabbit in half in any direction and by tracing a line passing through the origin. No matter how it is divided, it will reconnect itself using these operations. What matters is that out of the 2 symmetric points, we choose one. Not only is Z to Z squared plus Z applied within the rabbit, but it is also used outside of it. To study it, we will borrow vocabulary from the field of electrostatics. We can imagine a capacitor composed of a prism profiled precisely to have the rabbit as a section. There, we can observe potentials and equipotentials. Equipotentials are simply the curves we used to color the blue area depending on how fast the points escape the screen's borders. We can construct not only this, but also a system with an external caret, just like we did for the internal carets, by taking a segment off the real segment on the top right, and doing the same for its reciprocal images. This will define a more precise graduation of the rabbit composed of outer radiuses, which are nothing more but the electric field created by the receptor. This allows us to define for each external point an external argument, which will itself define a moment at which the radius will cover said point. This external argument rotates around the rabbit in an irregular manner. Sometimes it glues to the peaks, but it also sometimes whips the gaps swiftly. This is where the famous power of the spikes comes from in the electrical field of things. We then obtain analog coordinates on the outskirts of the rabbit that are analog to the coordinates of the outside of a circle. The dynamics outside the rabbit is defined as follows. We can locate a point using its potential and its external argument, just like you can locate a point outside a circle using its modulus and its external argument. Although, it is better to think about the logarithm of the modulus, which is what will play the analog role of the potentials. Once we compare the two grids, there's a correspondence between the rabbit and the unit circle that corresponds to z gives z squared plus z for the rabbit, and z gives z squared for the unit circle, meaning it transforms the first operation into the second one, although the second one is much more understandable, making it easier to understand the dynamics outside of the rabbit. On the outside of the rabbit, the arguments 1/7, 2/7, and 4/7, when all connected, create the alpha point. We define a relation of equivalence between the angles by saying that two angles are corresponding if the external arguments of the rabbit end in one point. Therefore, the points 1/7, 2/7, and 4/7 are equivalent, and will be represented on the unit circle using a curved triangle. Another example, the points 1/14, 11/14, and 13/14 are equivalent, allowing us to create another curved triangle within the unit circle. We then end up with an infinity of correspondences, each represented on the unit circle with a triangle. We can consider this as a correspondence of equivalence on the unit circle by saying that each of those triangles is a class of equivalence. If we contract all the points that lie on the unit circle, we recreate, topologically, the rabbit.